Right, welcome. Today we're going to functionally quantize the Dirac field. In the previous lectures, we've been building this theory of Grassmann variables or Grassmann numbers. And so far, this is just some mathematical curiosity that we've been playing with. Today, we're going to put it to some use to build a path integral-like object that provides us all the endpoint correlation functions for the Dirac field. So we ended last lecture, and indeed, it's one of the exercises to compute the generating function for the Grassmann Gaussian integral. So if you, where do I have it? If you have a Grassmann integral over n Grassmann variables, and, well, these are now complex Grassmann variables, theta j star. Remember, we have the relation that these things anti-commute with each other. Then we can define something that looks very much like a Grassmann, a Gaussian integral. And we've learned how to evaluate this object using this definition we built for the integral here over Grassmann variables. And to make this really useful, we're going to actually add a linear term just as we would for a normal integral over normal variables, a normal Gaussian integral over normal variables. So there is a summation convention in force here. And we can build the following object. This is something you can do. You're very welcome to write down these expressions, and you're very welcome to use the definition of the Grassmann integral that I introduced in the previous lectures. And just looking at it, that looks exactly like the generating function for a Gaussian integral. So, you know, as written on the board, it is simply the generating function. And then if you use the rules that we introduced to evaluate Grassmann integrals, then you come up with a formula that's astonishingly similar to the standard Gaussian result. Now, there's a couple of points to notice here, of course. These j's themselves are Grassmann numbers that anti-commute with everything around.
Sorry?
Yo, a question?
A star by the last theta.
Did I miss a star in the last thing? I certainly did, thank you. That's got to be a theta star, hasn't it? Yeah. And I've used a shorthand notation here already. This stands for that bunch of Grassmann objects. So also we have here this matrix B in this generating function is Hermitian. Oops. So you are all more or less aware of this result now. If you haven't done it already, then you will do it, and then you will be able to use it at your leisure. This is the basis for the functional integral quantization of the Dirac field, this single result here. We'll get to that in a second. I just want to point out one thing, and that is that you do get numbers at the end. You know, the input here is this object Z takes a vector of Grassmann numbers or Grassmann variables and produces something involving a quadratic expression of these Grassmann variables here. And these things commute with each other, so these will produce numbers at the end of all of our computations. So even though the input looks like an anti-commuting object, the output will always be a commuting thing. So we're never going to, importantly, right, we're never going to get as a prediction for an operationally defined quantity that the expectation value is a Grassmann number. That should never happen. If that happens, then you know you've done something wrong. So the expectation values of observables in quantum mechanics are always real numbers. That comes from the fact that observables are Hermitian operators. So if you've done a calculation and you get a Grassmann number as the answer, then you know you've done something wrong. So this is a super general result that I've written in the box there that you can apply in any number of circumstances. And you can have a lot of fun just developing the theory of Gaussian Grassmann integrals. Think about defining combinations of Grassmann objects and normal objects. And then eventually you can build a whole analysis, whole theory, whole body of mathematical analysis that's centered on these Grassmann objects. You can certainly do that. There are books written about that. In fact, they're quite beautiful in their way. I guess I should mention too, if you're interested in the mathematical side of things, so the one that is most often quoted and it's a very nice book indeed, very clean, clear, and precise. He develops the whole theory of Grassmann integrals within this book. There's the book called The Method of Second Quantization by Berezin. There's also another one, which I rather like. It's a bit harder to get. And Lightus. I mean, the title will get you there, but the author's help. So the introduction to superanalysis, also you could read this second book without knowing the first, but it certainly helps to have read the first book. In the second book here, they go completely crazy. This is fantastic. They take everything that you would know from normal analysis with real variables and generalize it to Grassmann valued objects. And they go all the way from the real numbers through to what a manifold would look like if it had Grassmann coordinates, through to all number of crazy vector bundles on top of these manifolds and so on. So you can really take this a long way and develop some very interesting mathematics. And indeed, it would be fun to spend a whole semester doing that. It's undeniably very attractive. We're not going to do that. We're just going to use these objects as a means to an end, namely to build something that looks like a path integral, to provide us with the Green's functions for the Dirac field. So I better actually get on to how we do that. We're going to have to talk about fermions at some point, so let's get it out of the way. Dirac fermions, Dirac spinor fields. This is classical at the moment. So what are they? Well, they four-component objects that depend on space-time and that furnish a representation of the Poincare group. So we discussed that in the last course. So this is the representation of the Lorentz group. The Poincare group follows pretty easily from this. And remember, we had these S mu nus, and these psi's were four-component vector things. So psi's are four-component vectors, the elements of the four-component vector space, but they transform as spinors, which means they transform according to this representation of the Poincare group, or Lorentz group, for the moment. And these S mu nus were these commutators of these gamma matrices. There's ion 4s in there, yep. Just like that. And the gamma matrices, yeah, I may as well just write them out as well. These are these objects that fulfill some anti-commutation relations like that. So this was discussed at length in the previous course. If you can find some matrices that obey this anti-commutations relation algebra, then you can build these objects S mu nu, which in turn give us a representation of the generators of the Lorentz group and also the Poincare group. And then any object which transforms in this way anything we define to transform in this way according to this representation here, this 4x4 matrix, we call a Dirac spinor. So there you go, done. That was our quick reminder of the Dirac field. Now what's the generator of time translations? Well, now that you know this, you could derive it by simply working out the representation of the time translation generator. I'll save you the bother. The Dirac equation is this equation here. Is it minus? Yeah. And we define this psi bar thingy, which is psi dagger gamma naught, and then that equation comes from the following Lagrange density. where the slash notation I'll put in the box here means that, of course. Yeah, so now we've done our full little reminder. Of the Dirac, single particle Dirac field. What we're going to do now is we're going to build a classical field-like thing. So we know that ultimately the Dirac field in the quantum world is a fermion. So all these, when you quantize or when you guess this quantum theory, these psi's correspond to like operators. I mean, they're distribution value, but they correspond to operators that anti-commute with each other. So the classical limit ought to be, morally speaking, something that anti-commutes full stop. So this is all single particle. And now let's build, and up to now we've been considering this thing here, this this spinor valued object that depends on space-time. We've been really thinking of this as the classical Dirac field, but what I'm going to tell you is that that's not the right way to think about this. This is the single particle guy. To build a classical Dirac field, we should really want it to be anti-commuting, because we have this, remember when you quantize the Dirac field, you have this you quantize the Dirac field according to the anti-commutators. There's no I there, is there? Let me check that. Okay, I can't for the moment remember if there's an I there or not. I don't think there's an I there. Does anyone remember? Is there an I on the anti-commutation relations for the Dirac field? Don't think that there is. Ah, I know what's wrong. Yeah. Now I think that's correct. So when we build a quantum theory for the Dirac, okay, when we build a quantum theory for the Dirac field, we look at our classical single particle theory, we put hats on the size, we come up with some algebra that we want our field operators to obey, and then we look for representations of this algebra. So that's the approach we took in the last course. And that led us down the path of creation and annihilation operators and so on. But here's a bizarre alternative reality where we could do quantum field theory with Dirac fields. In this bizarre alternative reality, we imagine that we have some classical Dirac field that we then quantize via the path integral. So this bizarre alternative reality, we think that we discovered classical fermions first, and then we build quantum fermions from classical fermions. This is not how things went, of course. But you could imagine doing things this way, and there will be lots of advantages to doing things this way later in the course. So in the alternative way, we find some classical Dirac field which we then quantize via the path integral. Now, you know what I think about the word quantize. I mean, ultimately, the path integral is just a way to guess quantum theories. So, guess number one, which is wrong, is you let the classical Dirac field just be psi of x, normal number, normal vector, a normal spinor. So we have this Lagrange density here. We could stick in to the path integral prescription this Lagrange density. We could integrate over all these psi's. And then we could use that as the basis for a quantum theory, right? But if we did that, horrible, horrible things happen. So it's a good thing to try, but I don't advise it. It doesn't give the right answers. You do not get out the endpoint correlation functions for the quantum Dirac field. You get other stuff out. And of course, what you get out are bosonic correlation functions, because you've treated this field as a, when I say normal number, I probably should have done this. Bosonic. So if you treat the classical version of the Dirac field psi x as like just a normal bunch of numbers that depend on space-time, stick it in the path integral, what are you going to get? Well, the path integral thinks it's a boson. Boom, you get bosonic quantization of the Dirac field. So we know what goes wrong there. We've been down that road, so we don't want to go down that road. We know that this is not the right way to proceed. So guess 2, which is correct, is to define the classical Dirac field to be Grassmann number valued. It's a bit, yeah. It's a bit mind-boggling to imagine what that thing is. Although if you know about sheaf theory, you can make a lot of sense of this very quickly. It's very easy to make mathematical sense of a Grassmann valued field. So this works. So you define some Grassmann number valued field, and that you simply declare that to be the classical Dirac field. And obviously this works, otherwise I wouldn't have taken the time to introduce these Grassmann numbers. So I've got to show you how to make something Grassmann number valued. And then once I've shown you that, you'll know how to do the path integral. Okay, the correct way to do this is with sheaf theory, but I'm going to give you a shim. We'll just use the lattice discretization, because in the end, the only way we can deal with the path integral is via the lattice, or with some other cutoff. I don't know. Someone might be interested in following this up. You can find this in this book on Introduction to Superanalysis. The correct way to deal with Grassmann number fields is you introduce a thing called a ringed space to a manifold, and that object is this particular sheaf, which is this ring space. You can assign to the rings involved in this definition the ring of Grassmann numbers, tensor producted with the normal functions. So that actually works. It works extraordinarily beautifully. However, we won't need this super sophisticated technology to do the very basic calculations that we want to do in this course. So that's the correct way. Here's the alternative way, which is also correct for discrete things. And yeah, just a warning, if you do want to invest all the time to learn sheaf theory and ring spaces and so on, that won't help you when it comes to the same divergences that we encounter in the bosonic case. All this beautiful maths is of no use whatsoever, because the divergences you'll encounter, which you will encounter when you do a path integral over these spaces, are just as problematic as the bosonic ones, and they need another tool to solve, which we're going to deal with after this, after we've quantized the Dirac field. So here the idea is we take psi of x, what is this thing? And x is an element of space-time. And we're going to discretize space-time. That's the first step. And we're going to discretize it all the way onto some torus. N sites. This is what we did before for the bosonic case. So we can label the sites if we like, all the way up to n minus 1. And these sites are arranged on a ring. And, well, I've only drawn one dimension here. This is the 0 plus 1D version. So the 0 plus 1 dimensional version of discrete space-time is a ring of n sites. And so there's a lattice spacing that we have between these sites. The lattice spacing is epsilon. And we introduce some variables x. I want to write j, but it's going to get me into trouble. And I guess I'll go with j. So j is a list of 4 integers, epsilon is the lattice spacing. This is exactly how you would, the naivest way you would put a Dirac field onto a classical computer. Like a classical computer can't store continuous variables. There's always some finite level of accuracy. And so you have to discretize your spatial coordinates. And the naivest way is just stick it on a lattice and then make that lattice wrap around when the variable gets too large. This is basically how you, this is not, the actual way you would discretize the thing is not much more sophisticated than that. Good, so you discretize space-time like this, and then, now we're almost there. So then you define psi j to be psi evaluated at epsilon j, or in some average location around epsilon j. And psi j is itself is a list of 4 things, right? Because it's a spinor now, it's not just a boson field. So this is precisely the moment where we're going to get into trouble, because I want to find a symbol to denote the 4 components of this thing. Oh, let's use lowercase, a. That should work. So these things here are then Grassmann numbers. Done. That's how we're going to define the classical Dirac field. We don't define it as a field because that would lead us down the road of sheaf theory. We define it instead on the lattice, and all it boils down to is per lattice site, or lattice cell, more properly per cell, we have a list of 4 Grassmann numbers. Psi j, a equals 1, a equals 2, a equals 3, and a equals 4. And then of course we have their complex conjugates, or their... We also have to define psi dagger, j. And again, we do so by a list of 4 complex Grassmann numbers like that. So that's how we're going to define the Dirac field, the classical Dirac field. It's a list of let's see if I can count this correctly. So depending on your programming language of choice, lists might be delimited with curly braces. Actually, I can't think of a programming language off the top of my head which does that. Let's do it in JavaScript. Here we go. Or if you want to use JSON, then of course we could use the curly braces. Or in Lisp, we would have curly braces and so on. So it's a list of these things. And how many are of these Grassmann numbers? Well, there's n to the power 4 sites. Times, at each site we have a list of 4 psi variables and 4 psi star variables. But remember, these are absolutely they're just independent Grassmann numbers, psi and psi star. So it's actually a list of 8. So it's So a classical Dirac field for us is a list of n to the 4 times 8 Grassmann numbers. You can actually imagine putting this into a computer if n is sufficiently small. It has to be pretty small. Because to represent these Grassmann numbers, remember we need these matrices via this Jordan-Wigner type transformation, and they themselves take 2 to the whatever this number is dimensions to write down. So I don't advise actually doing this for more than, say, 2 sites. 2 to the 4 is 16, right? Yeah. Those would be enormous matrices already. So in 4 space-time dimensions, it's pretty tricky even to record a classical Dirac field on a classical computer. So the utility of these things classically isn't so good numerically, but we'll do some steps and see that we can produce something that we can do numerically pretty easily. All right, that's a classical Dirac field. And so, well, discretized. And so the continuous classical Dirac field is, if you can imagine it, where epsilon tends to 0 and n tends to infinity, and L, the size, also tends to infinity. And the size is n times epsilon. So if you can imagine that, that's what a classical Dirac field is. An alternative way, which I won't bother pursuing here for the moment, would be to do everything in momentum space. And yeah, I guess I'll have to do that later on anyway. If you do things in momentum space, you impose you have to discretize somehow. You have an infinite number of modes, so you just truncate your description of your classical field up to some number of Fourier modes and make the Fourier coefficients Grassmann number valued. That's the way to make a classical Dirac field in momentum space. Make the Fourier coefficients Grassmann number valued. But for the moment, I quite like real space lattices, so let's stick with that. So up to the word continuous, that's actually, there's no harm in thinking of this as being completely rigorous, what I've written up to here, up to the point where I say continuous. It's a finite number of Grassmann numbers. How do we build now a quantum theory corresponding to this classical object via the path integral? Well, we need an action, or at least a Lagrange density. Actually, those of you who know about fermion doubling are going to see something, have probably already noticed that we're going to run into problems if we do things in this particular way. To that I have no answer. If we do things on the real lattice, we're going to encounter a thing called the fermion doubling problem. I don't want to dwell so much on that in this course. I'll point out the moment when it happens, and I'll also describe how I get around that problem. So we need a Lagrange density. Well, we have one, but that's for the continuous ones, right? We've got to discretize. And we end up with a sum now. And what's the right way to do this? I guess psi j plus mu hat. So when you discretize, you use you replace derivatives with discrete derivatives. And we get some object like that. Now this is quadratic. Remember now, these are all Grassmann numbers, right? So it's some object, this discretized Lagrange density, that depends on Grassmann numbers in a quadratic way. Now we have enough to write down something that looks like a path integral for this guy. So this mu hat, well, this mu, I'll put a mu here. Mu hat is just the unit vector in the muth direction. Yeah, a question? The question is, you don't. Oh, there's some gammas missing, actually. Yeah. So what was the other thing missing?
The discretized derivative, I don't see this. Where's the other term? Minus to subtract.
Oh. All right. So the question was, I didn't. Where's the other term in the discretized derivative? Yeah. Okay. I made some mistakes here. Can it be rescued without too much erasing? Let's see. I'm going to put back all the same information, so I hope it's. So the point was I didn't discretize the derivative correctly. Let's do it correctly now. Firstly, there's some gamma matrices missing. Okay. Oops, they're going to have upstairs index. So that was a problem already with this discretized action that I wrote. And now we've got to do the actual difference. And don't put hats at all. Okay, I hope that now is a proper discretized derivative. There's gamma matrices, there's a forward difference, there's a number I, and why did I put a minus sign there? Let's put a plus sign there, and I think it's all good now. Good. And then we have the other term. I just so want to write that hat. Okay, is that correct? It's one way to build a discrete action. And now we have all the data we need to define something that looks like a path integral quantization recipe. So it's a definition. I'm not going to prove this, I'm going to define this, and then after the fact confirm that it does everything that we want a path integral quantization to do. Here we go. So we're going to define the I'm going to try and do this in the least painful way that I can think of. So let's make this 0. The 2-point function if we were just proceeding by analogy with the bosonic case, then we would write for this some limit some path integrals So if we want to know the time-ordered 2-point correlation function for the quantum Dirac field, and we wanted to do it via a path integral, then if everything was done correctly, we should be able to just copy the expression we use for the bosonic case. Now at least we've reached the point where we can interpret each of these terms. We can provide a way of actually calculating this. How would we calculate this? Well, how have I told you to calculate normal path integrals? The answer is, of course, discretize, evaluate, then take the continuum limit. So I've given you the method for discretizing psi. I've given you the method for discretizing L. I've given you the way to carry out integrals over these Grassmann numbers. So all that really remains to be done is to carry out those steps and hope that we get the right answer. So that all this work was worth it at the end. So discretize, evaluate, take the continuous limit. That's our next step here. And you will get the answer. It's a lovely exercise for you to do this. All right. So there's a subtlety here. And I think it's fair to say this is still an open problem, an open topic of research. And it's called the fermion doubling problem. If you define fermions on a lattice and then take the continuum limit, then you get a second fermion that doesn't go away in the continuum limit for every dimension. So this is a warning to those of you who might want to do this numerically. So I'll say a couple of very vague words about this problem, but I claim it won't be an issue for us in this course. If you define quantum fermions on a lattice and then take the continuous limit, you're going to get extra fermions in the continuous limit called doublers. And this comes from the dispersion relation. So you can think of this as a topological result. If you put fermions on a ring, then the dispersion relation has to cross the real axis twice. If you put fermions on a ring, there's no way around it. The momentum has to come up and join itself again. The energy has to be continuous. It's going to cross the real axis twice. Now the dispersion relation, I've drawn it in the wrong place. So the dispersion relation for fermions on a lattice looks like this. This point is identified with that point there. Because remember, when you put something on a ring, then in Fourier space you also compactify the momentum space. Now, this is the dispersion relation you want for Dirac fermions is this straight line here. That's the dispersion relation. When you solve the Dirac equation, you get that the energy depends linearly on the momentum. And you might hope that as you take the lattice spacing smaller and smaller and smaller, that this sort of better and better approximates this linear dispersion relation here. Indeed, that's correct. It actually does, right? But you can't ever get it to not cross the x-axis over here. Now that means that this is the low energy sector that that should map onto the continuum limit, but there's this other sector over here. These have also close to zero energy excitations over there, and they never go away in the continuum limit. So for every one of your original fermions that you define, you pick up this extra guy that's an independent low energy excitation, and it doesn't go away. This is a second independent fermion. Now we don't observe these doublers in nature, so we're pretty sure that fermions don't live on lattices in nature, or didn't come from something that lives on a lattice. Now it's a tricky problem to deal with, and it tells us that we have to be particularly careful when evaluating these kind of things here. So if we do the definition, if we do the limits in the wrong way, we're going to have fermion doublers when we do these, evaluate these path integrals. So if you evaluate this path integral, if you think of doing the quantization recipe by discretizing everything onto a finite lattice, then evaluating the path integral all the way down, getting an answer, and then taking the continuous limit, you will end up with fermion doublers. Yep, a question?
Energy is discretized, so if you discretize energy, then don't we get a closure on the omega axis too, and so there would be the possibility of the winding?
So you say, so the question was, if we discretize energy, don't we also compactify in the energy direction, which is conjugate to time? Yeah, we absolutely do. And you can get horrible non-trivial windings. That's exactly the case. So it only gets worse if you discretize time or energy. So discretizing time is equivalent to compactifying energy and vice versa. So that problem doesn't go away, it only gets worse, because you can wind around more directions. So the bottom line is, if you do it this way, if you think of a Dirac field as being the continuum limit of just a bunch of quantum fermions on a lattice, then you have to explain why these doublers aren't there. And people have come up with sort of increasingly Baroque constructions to get rid of them, but the fundamental problem is still there. It's a research topic, it's not solved. So we're going to be a little bit sort of sneaky in how we do this integral here. We're going to take the continuum limit during the integral process. We're not going to do the continuum limit at the end of doing the path integral. We're going to, as the intermediate step, we take the continuum limit. And so I'm going to sort of say, it'll be fine. You know, we won't, we're not going to have to encounter this fermion doubling problem. However, you have to be aware that it's absolutely there if you define things on the lattice. And it doesn't go away if you go to momentum space. So people might argue, I've heard people argue, you just go to Fourier space. There, space is continuous, you won't get the doublers. You actually do get the doublers, but now you get them in momentum space. You can't get rid of it so easily. It's an annoying subtlety, and it gives us a decision that we have to take now, which is, do we work with these path integrals formally and accept the results by working with them formally, or do we insist on discretizing everything and taking the continuum limit only at the end, in which case we have to accept we're going to get these doublers, and we have to think of a way to get rid of those. So if we go to the first way by interpreting the path integral formally, then we have to start doing non-rigorous things. We just have to do manipulations that work, that we accept the manipulations by analogy with the bosonic case. Or if we go the discrete route, we have to accept these fermion doublers and then explain those. In this course, because the path integral is a tool, I'm going to go the former route, which is to say, we learn how to use it as a box. We learn how it produces, endpoint correlation functions, and we just accept its results. And anytime you're unsure about the validity of a manipulation, then canonically quantize and do it the hard way. Okay, we come to the last topic for today. Now we learned that all the correlation functions you could ever want can be obtained from a Gaussian by learning how to compute the generating function. And for the bosonic field, we've done it the hard way, and we've also derived the generating functional directly in the continuum for the path integral. And once you've got the generating functional, then you can do everything. You just because all you need to do is differentiate rather than integrate. There it is. There's the generating functional for the Dirac field. If we could compute this object, then, well, we'd be in a great position because we'd be able to get all the endpoint correlation functions just by differentiation. Now, this is I guess, for me, the best moment in going through all the trouble with Grassmann numbers and Grassmann variables, because we're going to get a result that's fantastic, that just summarizes all the mysteries that we saw in the canonical quantization route. Okay, these J's, these are source fields, and they're Grassmann valued. There's these auxiliary fields that you add in, and you're going to differentiate with respect to them and then set them to 0, and that'll give us the correlation functions. All right, so how do you do this thing? Well, you know how to do this, right? How do you do any generating functional computation with Gaussians? You complete the square, and a little exercise later will lead you to the following expression. It's exactly the same computation as what we needed to do for the bosonic case. There are absolutely no differences. And this Z0 is what you get, is this divergent piece, what you get by setting J to 0. And this next bit is just so wonderful that it's worth all the trouble, in my opinion. So we have this generating functional. We know that we've defined the path integral quantization for the Dirac field. We want to get endpoint correlation functions. Well, if you were to do things by canonical quantization, what we did last semester, then you encounter, when you want to compute these endpoint correlation functions, you encounter the difficulty that you have these minus signs everywhere, right? If you want to, we have a Wick's theorem for Dirac fermions. We worked it, I mean, I just quoted it. It was really painful. There were minus signs. You had to remember how many times you exchanged this and that to compute these endpoint correlation functions. And I didn't even bother proving it in the previous course. Here the proof will occupy 1/4 of the board. It's just astonishingly simple and follows just by the rules from Grassmann derivatives. Recall so if these two guys are Grassmann numbers, then the derivative of an expression such as theta eta is minus the derivative of theta times by eta, the derivative with respect to eta. So just this simple observation here is what fixes up all our, or takes care of all those minus signs and permutations and worrying about the order you do things in. Because as long as you remember the rule for Grassmann derivatives, you're golden. So endpoint functions Now, there's no good notation for daggers or psi bars. So I'll just use alpha. So where psi alpha x is psi of x, or psi bar of x if alpha equals 0, alpha equals 1. Because you need to be able to put in psis and psi bars. Not, that's J. Okay. One has to be a bit careful about the signs. I'll just rewrite this. So we have to bring down these psis and psi bars in here. And we have to worry about the fact that we pick up a minus sign when we differentiate these guys, because we move past the psi bar in this particular case here. So we have to deal with that by having this sign correction there. But otherwise, that's the answer. You get these endpoint correlation functions by functionally differentiating this thing here, just taking a little bit of care of these signs there. And then, for example, the 2-point function works out as you hope. And you also have the fermion-Wicks theorem for free once you've got this, this generating functional here. All right, we're going to take a couple of minutes to talk about how we use this to deal with interacting theories. And then we're going to move on in the next lecture to the topic of renormalization. So you should think of the path integral as a kind of Wick's theorem generator. You input a Gaussian theory and it outputs the correct Wick's theorem for you. And once you've reached that point, adding interactions proceeds just as we did in the previous course. You put in some terms in the Lagrangian that are nonlinear, you do a Taylor expansion, and then you encounter higher and higher endpoint functions, which you then use the path integral to apply Wick's theorem to. So there's nothing more to interacting quantum field theory in the perturbative limit than just repeatedly applying Wick's theorem. The Feynman rules are a way to collect together the patterns you notice in applying Wick's theorem to a Taylor series. So we're going to just very briefly sketch a reasonably complete approach to a perturbative quantum field theory using the path integral approach. Like, how would you just do it in practice? And I'll do it for the example of massive quantum electrodynamics. How would we use all this cool technology that we've developed? Well, the path integral is a Wick's theorem generator. So all we're going to do is use it to guess the Feynman rules. And once we know the Feynman rules, we won't ever bother looking at the path integral again. We'll just use the Feynman rules. So that's what the path integral is good for. It's very good for efficiently guessing Feynman rules. Now, we're not going to do QED yet, proper QED, because we haven't done gauge theory. And I'd prefer to do gauge theory first before we do QED, so that you see things like in the correct order. However, there's a way to do something that looks very much like quantum electrodynamics, and that's called massive quantum electrodynamics. So in massive quantum electrodynamics, you have this gauge field A, which is just a bunch of 4 boson fields. So we know what to do with bosons, we're good there. And we have some action for this gauge field. And the action is the Maxwell action, which has a gauge invariance, which produces all kinds of interesting divergences in path integrals. So we're going to talk about those in the second half of this course. However, you can get rid of all of them, all those spurious divergences, by adding a mass term to this gauge field. So what that's doing is effectively saying that the photon has a mass. And if you do that, if you take if you add this mass term here, then you don't have to worry about gauge invariance. This is already wrecked gauge invariance, so we're going to... Yeah, a question?
There should be a difference between the capital M and small m. Or
There
should be the same mass.
This looks like an M, doesn't it? Sorry, this is meant to be a mu. Yeah, the question was M in both M's. Shouldn't they be different? Indeed, this is the mass of the fermion in quantum electrodynamics, the electron or the positron. This is the mass of the photon. Now we know that the photon's massless. Well, do we? Actually, I looked for experimental bounds on the mass of the photon. It's about 10 to the minus 54 electron volts or something. So there's apparently you can collect together cosmological observations and a bunch of other observations to derive bounds on the mass of the photon. And the best bound we've got is like 10 to the minus 30, 40, or 50 electron volts. I can't remember the exact number. It's extraordinarily small, but it's not zero. So we don't actually know for sure that the photon is massless. But, you know, the universe would look pretty odd with a massive photon. So this is a possible physical theory of reality. It's not the one we find ourselves in, or at least we do not think so. How might we do the whole path integral quantization game now? So we write down our fields. We have a spinor field, and we have 4 bosons. There they are, 4 boson fields. So we know what to do with these. Boson fields are good, and we know what to do with fermions. So why don't we just write down a path integral quantization recipe for this theory? Maybe it works. Oh, I assume you know what F mu nu is. Right. I've got the quarter there, so I think that's correct. So this is some second order thing. Good. How would we quantize this? Well, we have these fields. We need to integrate over them. So we have some vacuum expectation value. Let's focus on, say, let's suppose we don't have a process where we're observing photons at the end, but simply fermions. You know, what's the probability amplitude to go from a fermion at x to a fermion at y? And let's use the path integral prescription to do this. Well, path integral prescription says integrate over your fields. Put in the action. And insert these fields over here. So this is like great, very compact. I mean, I didn't even look at my notes to write that down. I knew that would be the answer. And this is very good for exam preparation, by the way. You know, you only need to remember how to write that down, and you could probably get your way through to the answer. What are we going to do now? Well, the action S breaks up into the easy bit plus the hard bit. The easy bit is the action for the fermions and the bosons, and the hard bit is the interaction. So we only have one interaction in this whole story. It's kind of a bit buried in here. I don't have any colored chalk. So here's the interaction here. This is the only place where the bosons talk to the fermions. Everything else is just Gaussian stuff. So let's write that out. Here's the Gaussian stuff. easy bit. And here's the hard bit, which is so I'll write it like that. There, this is the hard bit here. Well, this is Gaussian. And this is small. E is fine structure constant, which is 1 on 137 approximately. So it's really small, right? We can expand in the smallness of E. So our two-point function we can evaluate it by using Wick's theorem, which is otherwise known as do the Gaussian integral, applied to e to the IS naught, and we Taylor expand the hard bit. It's the only difficulty we need to worry about here. So we have the easy bit, that's like the Gaussian measure, and then we have this Taylor series here that deals with this nasty term. All over the same thing on the bottom, but without these insertions. Oh, I forgot those. Now the zeroth order term is a Gaussian integral. You can work out the generating function. You can evaluate it. You get the number 1. Oh no, you get SF as the answer, sorry. Good. So this is an infinite series of correlation functions for Gaussian functions, or endpoint functions for Gaussian. Now, when you look at each of those terms in this infinite series, then you'll notice some patterns, and you'll deduce that the terms in this series can be represented by diagrams, and those diagrams obey some rules. And here are the Feynman rules that you'll notice. You draw for fermions straight lines photons with mass, you draw wavy lines. You label them with momenta. And also with indices, mu, well, A I guess we'll use. And we associate to each fermion line A, B, mu, mu. The propagator, I'll use P, so it's P slash so to each fermion line you associate this propagator here. This term will appear corresponding to that diagram. And to each photon line, I actually don't have it written down. I use, make that a K. Okay, I'm not sure if that's actually correct for the photon lines. I didn't write that one down. So you need to check that. With each vertex, we associate a factor of e to the I gamma mu. We impose momentum conservation. By summing in the in momentum and the out momentums and making them zero. You integrate over undetermined momenta, one per loop. You amputate external lines. And you associate a factor. Oh, yeah. Then there's incoming fermions. Get e to a's. And -1. I made a mistake here for the photon line. I'm sure there's more than one. It's mu squared, obviously, not m. Not to be confused with a mu on the propagator. It's ugly. Right. So you go through, you expand in powers of E. You encounter an infinite series of Gaussian integrals and endpoint functions thereof. You evaluate them using the generating functional. And then you have an infinite series of terms. And you have to organize those terms. You can forget the Feynman rules and just deal with each term as it comes. Or you could use the fact that you can sit down and do the combinatorics once and for all and realize that the only terms that actually contribute are ones which obey these rules, and then evaluate those. And what will happen after you do all that? Well, you get the number infinity straight up. So something's wrong. So after all this effort, we've come to an answer, and the answer is infinity, just as it was in the first semester. So we could have summarized the whole course of last semester and up to now with every transition amplitude in interacting theory equals infinity, and the only difficulty is working out the plus or the minus sign. So you could dismiss everything we've done like that. However, it will work, but you have to change the way you approach these calculations, and in fact change philosophically the way you regard these fields. That's a topic for the next lecture. I've already given you in the previous course a small summary of what we call renormalization theory. I'm going to repeat it again, and then we'll get into the actual details of how you implement this renormalization theory, beginning with the next lecture. But for now, we've actually completed our tour of path integral quantization for fermion and boson fields. The only field we haven't discussed yet are gauge fields. That'll come after renormalization. Okay, so thank you very much.